In this lecture, we're going to consider two interesting questions about infinite sets, and that's going to lead us to Cantor's theorem and the continuum hypothesis. So before we do that, let's just recall really important and useful notation. So given some sets, A and B, possibly infinite, we say that A and B have the same cardinality, and this is how we write that. Absolute value A equals absolute value B, but this means they have the same cardinality, which means there's a bijection. There exists a bijection. So if there is a bijection, it does not mean they have the same number of elements. So that doesn't make sense for infinite sets. So if there's a bijection, from one to the other, we say they have the same cardinality, and we indicate it like this. Okay, so a little bit of confusing, this notation, because this equal sign. It's not the true equal sign that we're used to. It's not saying A has the same number of elements as B. It's just notation indicating there exists a bijection from A to B. And there's a good reason, actually, that we use the equal sign. So the reason is it behaves like this kind of thing behaves like an equal sign. In other words, it's an equivalence relation. So this is an equivalence relation on sets. It is reflexive, symmetric, and transitive. Okay, this existence of a bijection from one set to another, and that's actually a great exercise if you want some practice with equivalence relations. Try to prove that this is an equivalence relation on sets. Okay, but that's why we use the equal sign. So it behaves like we'd expect an equal sign to behave. Similarly, so this is a new notation. We say we can use other symbols, and this is when we want to compare different sizes of infinities. So we say A is less than, let's do less than or equal to B, absolute value B, if, what should this mean? Well, it shouldn't mean that A has fewer elements than B, because again, that doesn't make sense for infinite sets. So let's try to phrase it in terms of a function. And it turns out the way to phrase this is, so if there is, actually a couple ways we could do this, but one way is if there is an injective function, so an injection from A to B. Here the order is important. This is not an equivalence relation. It's not symmetric. So if there's an injection from A to B. And the whole point of an injective function is it allows you to sort of view A as sitting inside B. Okay? It might not, so this doesn't necessarily map to all of B. It might not be surjective, but it's injective. You can kind of view A as a subset of B, or in correspondence with a subset of B. By the way, the other way we could have phrased this is, so note, this also implies that there's a surjection going the other way. So that's sort of the other way you could have defined this. A surjection from B to A. Okay, so why is that? Let me draw a little picture here. So we have A here, and let's draw B a little larger maybe. So A and B, and let's say we have some elements here in A, maybe a few more elements in B, just to kind of make the point here. And let's say we have an injective function from A to B. So again, that means we don't have to hit everything, but we have to make sure we don't have any collisions. So this one could go there, this one could go there, for example. So that's an injective function. Why does this imply that there's a surjective function going the other way? Well, if we have an injective function, you simply reverse those arrows. Okay? And there's going to be no ambiguity because it's injective. So everything's going to map to, well, everything in the range of this function is going to map to a unique element, to just one well-defined element. And the problem is we have these leftover ones here, but we can just send those anywhere. map these anywhere. So that's the idea, but this is a standard definition for this. So if there's an injective function from A to B, we say this. And alternatively, so also we say A is less than, cardinality of A is less than cardinality of B if, well, you can probably guess what that means. It means there's an injective function but no bijective function. So if, I mean, in other words, if A is less than or equal to B, but it's not true that A is equal to B. Cardinality of A is equal to B, so cardinality of A is not equal to B. Technically, I didn't define what this means, but it just means the negation of this. In other words, there's an injective function. There's an injection, but no bijection. Okay. And just to be clear, like I'm not saying that there's an injection that's not a bijection. That's actually true for any infinite set to itself. You can find a injection that's not a bijection. In fact, that's an interesting way to define an infinite set. But I'm saying there's an injection, but it is not possible to find any bijection. Okay, so these two things. Okay, what's an example of this? We've seen an example. We saw one in a previous lecture. Cardinality of the natural numbers is strictly less than the cardinality of the real numbers. Real numbers have a greater cardinality, and there is no bijection from n to r. Yet there is an injection, right? You can just map every number to itself. And yeah, so these symbols are great because they allow us to really easily talk about different and compare different sizes of infinite sets. Okay, and they allow us to phrase some questions. There are many. That's the thing about infinite sets. So when you start thinking about them, you always end up with more questions than answers. So. So we already proved this using Cantor's diagonalization. The cardinality of R is strictly greater than n. Maybe the next natural question is: is there anything bigger than R? So is there a set S such that the cardinality of S is strictly greater than the cardinality of R? Okay. And I mean, there's another related question too, which is there anything in between these? So n is sort of the smallest infinite set in a way. You can't really get anything smaller than n. If you try, it'll be bijective to n actually. But maybe there's something in between. Right? So is there a set S? How would we phrase that using our notation? Such that it is sort of sandwiched in between. So n, cardinality of n is strictly less than S. Cardinality of S is strictly less than R. Really great notation here. So, great. Let's try to tackle these questions. So the first one, well, what are some candidates? So let's try to imagine something bigger than R. How about the complex numbers? Or how about something like R cross R? Right? Product of R with itself. So pairs of real numbers. Or, I mean, what are other ways of getting something bigger than R? You could take the power set of R. Power set of R. That's actually a pretty scary set. What's the power set? Any the elements in the power set are subsets of all of R. So including infinite subsets. So this is a truly terrifying set here. That's why I paused. Just terrifying to imagine. power set of R. But in any case, yeah, so let's rule out these two, actually. So, in fact, I won't do this in detail, but it turns out, so I'll say it turns out that the cardinality of R cross R is the same as cardinality of R. And so is C, actually, cardinality of C. So complex numbers have the same cardinality as R. Why is this true? One way to see it is you can define a function from here to here that sort of takes the infinite decimal expansions of my two real numbers and interleaves them, sort of one place at a time. And it's not quite a bijection. You have to be careful about a few things, again, like the trailing strings of 9s, like we saw in a previous lecture. But that should at least convince you that this is plausible. And it turns out, yeah, you can define a bijection between these two sets. And if you can define a bijection between these two, right, then you can define one from the complex numbers. Because what are the complex numbers, really? You can sort of imagine them as just pairs of real numbers, right? Like here, a plus bi. You can view as, and people do view it this way, as a point on the complex plane, which is really just R cross R in disguise. Okay. So complex number you can view as pairs of real numbers. Okay, what about this third one, though? Turns out this one is bigger, so this is this is the one we want. And that is the content of our first theorem here, so Cantor's theorem. Let's state Cantor's theorem. And we'll prove it. Turns out the proof is pretty quick, so I can actually do the whole proof. I'm not saying it's easy to come up with, but it's quick once you have it. So actually, Cantor's theorem says for any set, not just R, but for any set A, let's just say, the power set has strictly greater cardinality. So strict inequality. So there's an injection from A to its power set, but there's no bijection. You can never find a bijection, no matter what A is. I suppose this even works for the empty set, right? Because the empty set has cardinality 0, but the power set of the empty set has cardinality 1. Because again, the power set of the empty set is this. This has one element in it, which is the empty set. Okay, let's prove Cantor's theorem. So proof. Well, the idea is, as in so many of these proofs, it's going to be contradiction. So suppose there is a bijection. Suppose there is a bijective function. So bijection from A to its power set. Okay, and we're going to try to deduce some contradiction. And this one is proofs. It's a little bit hard for me to remember sometimes because again, it's quick, but the idea is very tricky. So I think what you do is you consider the set. Let me write this set. So S, I'll call this, and it'll be some subset of A. So it's going to be all the elements in A that when you map it forward to its power set under the given bijection here, the element is not in the subset of A that it gets mapped to. So A is not in F of A. So what's going on here? Just give you an example over here. So this is not part of the proof, but it's just hard to kind of wrap my mind around sometimes. So here's A. Let's say it's 1, 2, 3. Let's say our function, it sends 1 to some subset of A. So let's say it sends 1 to like the subset 1, 3. And let's say it sends 2 to the subset 1. And let's say it sends 3 to the subset, I don't know, 3, let's say. And of course, this is not a bijection. That's what we're trying to prove, actually, right? But it's just an example of what's going on. So every element gets sent to a subset of A, okay? And there are some elements, perhaps, that get sent to a subset that does not contain the elements. So in this example, 2 would be in S. Okay. But 1 and 3 actually would not be, because 1 belongs to the subset it gets sent to. Okay, does that make sense? So that's the set S. And the trick here is S is itself a subset of A, right? So it's over here. It's sitting over here, and there's some element that gets mapped to it. So then there is some in fact, there's exactly one, because we're assuming it's bijection. So there is some, let's call it X in A, such that f of X is, so X gets mapped to exactly this subset. Okay, that's what we're. I mean, that's definitely true, assuming this. Okay. And now the trick is you ask whether this X is in the set S itself. So, and that's how you get your contradiction. So this always confuses me a little bit, but let's see if we can work through this. So. I mean, so first of all, since X gets sent to S, what does that mean? It means X is in this set, so in particular, X is not in S by definition of S, right? It's not in the set it gets sent to, which is S by definition of S. But wait, if it's not in S, so I try to write out as I'm thinking, so I don't lose a train of thought. So if X is not in S, what does that mean? Let's look at this definition again. So S is a set of all elements that are in the set they get mapped to. So if X is not in S, then it means X is in the set it gets mapped to, which is S, right? So X is in S. But if X is in S, then it's not in the set it gets mapped. So it's not in S. So we're in this loop, right? We have that X is essentially X is in S if and only if X is not in S. So there's a contradiction, right? Contradiction. So that's the idea. So yeah, you cannot have a bijection. And yeah, we're done with the proof. Or actually, I mean, just to be really clear. So what do we prove? We proved that there's not a bijection. Technically, when we say less than, what do we mean? I mean there's an injection, but not a bijection. So it's strictly smaller. It's not bigger, for example. So technically, to finish this proof, we need to show there's an injection. So also. Well, let's just define one. So G from A to power set of A given by G of X is, what should we say? Can we find an injective function from a set to the set of all subsets? So we just need to make sure there are no collisions. We don't have to hit everything. We can't hit everything. But yeah, how can we do that? Well, one way is just to send X to the subset X, right? The set X. Okay, that's a subset of A. So just send every element to the one element set containing it. So this is an injection, and that shows this. So now the proof is finished. Excellent. So this is a really wonderful and interesting fact. So it has a consequence, which is essentially there is an infinite hierarchy. Not only is there something beyond R, but there's something beyond that, and there's something beyond that. So there's an infinite hierarchy of infinities. And how does that work? For example, you could take n, and it's sort of the smallest infinite set. And that's strictly less than a power set of n. So it's all subsets of n, including the infinite ones. So this is quite large. But that is strictly less than the power set of that, the power set of the power set of n, right? You can keep going. Just keep taking power sets. And that gets you to a higher level of infinity. Okay. Oh, and by the way, this happens to be, so I won't prove this here, but this happens to be the same as the cardinality of R. Okay. So this is actually, same cardinality as R. And that's actually a good segue to our second question. So, well, that's the same cardinality as R. Is there something in between here? We didn't rule that out, right? We just we proved that this is larger, but there might be something in between. And that's our second question, the continuum hypothesis. So the continuum hypothesis. And by the way, this word continuum, I like the use of that word. It makes it sound really mysterious, but actually the continuum is just the interval from 0 to 1. So that first set, remember, that we proved is uncountable, so it has the same cardinality as R. Interval from 0 to 1 as a subset of R, so it's a continuum. Has all the numbers between 0 and 1. And so the continuum hypothesis is that there is no set in between n and R, for example, or n and 0, the interval from 0 to 1. Okay, that's the continuum hypothesis. You might note the word hypothesis. So is this true, right? Hypothesis is not a theorem. Well, this has a rather scary answer. So you might think that either answer is scary, like if it is true or if it's not true. Both those are quite hard to think about. Turns out the answer is even scarier than that. So this statement is what you'd say is actually independent. The statement here is independent of the axioms of set theory. Meaning, so in other words, it can actually be true or false. So it can be true or false. And neither will give you a contradiction. So it can be either true or false without producing a contradiction. You have to pick one or the other. But it can be true. And that's one version of mathematics, and it can be false in a different version of mathematics. So there are versions of mathematics where this is true, there are versions of mathematics where it's false. So you actually cannot prove this. It was proven that you cannot prove this from the axioms of set theory. That's what was proven. So it's actually independent of the standard axioms of set theory. And it's not like we're waiting for somebody to prove it one day. We actually proved that you cannot prove this one way or the other. Okay, and in fact, you can have it either way. And so another example of this, by the way, just to make it maybe a little bit less mysterious. So another example of this phenomenon. I don't know, maybe this actually makes it more mysterious. But it's Euclid's famous fifth postulate. So Euclid wrote the most famous math book of all time. Fifth postulate. We started with 5 postulates and then basically developed all of geometry from those 5. And the fifth postulate essentially says that parallel lines don't intersect. I'm being a little bit imprecise, but that's essentially what it says. And I mean, the first few postulates say things like between any 2 points, you can draw a line, things like that. Just really obvious things. And these are the 5 things he had to just lay out at the beginning, assume without proof. Then you can develop the rest of geometry from there. And what people realize is that this 5th postulate is it really does need to be a postulate. So people tried to prove it from the first 4 postulates and failed. And it turns out you cannot do that. So it's a postulate, and in fact, it's not always true. So it depends what kind of geometry you're working with. So this is true in Euclidean geometry. Right? Of course, parallel lines in a plane don't intersect. But it's false in other kinds of geometry. So it's false in hyperbolic geometry, for example. Which is another kind of math you can do. It has a lot of applications. It's also false if you consider lines on the Earth, right? Like parallel lines on the Earth, like lines of longitude. Well, those intersect at the poles. So it just depends what kind of geometry you're doing, whether this is true or false. And this is a similar phenomenon to that. So hopefully that kind of clears this up a little bit. But yeah, very interesting area of mathematics. Okay, so I'll conclude this lecture. Thanks for watching.